Okay, our next talk will be by Heino Falcke about the jet at the galactic center, the future role of millimeter VLBI.
Okay.
10 minutes.
Yes. Sorry for not attending yesterday. I still had to teach at our university. It's teaching season right now, and so I came in 2 o'clock this morning, so bear with me through this talk. We'll probably show. I was particularly happy that I was asked to give this particular talk because it said the jet in the galactic center. There was no question mark behind it, and there was no the jet model or something, so it was like a statement, the jet in the galactic center. And the reason why I was happy about this, because that's something we're working on the last 20 years. That's still a discussion, what is happening in the galactic center. And I'm firmly in the camp of those who believe that what we see there is actually indeed a jet, and therefore is well placed in this jet conference. And the background of this is more or less initially based on universality. If you look at accreting AGN, and particularly ones at low accretion rates, but not exclusively, obviously. Anton just talked about quasars, which obviously are high accreting. But if you look at AGN across, actually accreting black holes across the entire range, what you almost seem to find are flat spectrum radio cores in the very center. It's not always the most prominent thing to see, but they're always there, right? You go to a stellar mass black hole, especially in the low Hart state, it has a flat spectrum radio core all the way down to low accretion rates. You go to a very low luminosity AGN, it has a tiny jet, but it has a flat spectrum radio core. You go to an FR1 radio source, it has a flat spectrum radio core, and then the beautiful jet starts. And then, of course, the FR2 types, tiny little radio core, but again, and powerful lobes. But the core is always there. And and the reason why it's there is actually very simple, I think. And Roger Blandford Koenigsegg gave a very beautiful explanation how this actually works. And that was essentially my PhD thesis. Trying to understand what he did and then applying it to quasars. And the idea is very simple. You essentially pump some hot magnetized plasma into a jet. It will flow out supersonically. We essentially have a cone, a Mach cone, where the material will flow out. And then simply from mass conservation and magnetic field energy density conservation, you find that the density should go down as r to the -2 and the magnetic field as r to the -1. And then what you also have to take into account is optical depth effects. You'll see that actually if you're close to the black hole, density is high, the optical depth is very high. Out here, optical depth is low. So you get a tau equals 1 surface at a certain frequency. The spectrum that is emitted at this region will look like this, optically thick and then optically thin here. And then if you go closer into the black hole, the optical depth, the frequency where the source becomes optically thin moves to higher frequencies. And so going to higher frequency, you always go closer and closer to the black hole. That's again what Anton mentioned. And of course, if you go lower frequencies, you see something further out. And you can calculate this purely analytically. It's dirt simple to do. You find that naturally, if you do this with this scaling, you find a flat radio spectrum, you find a core shift, a size, which depends on frequency. The higher the frequency, the closer you get to the black hole. And also you find if you make some assumption about linear coupling, that's what we did 20 years ago, linear coupling between the power in the accretion disk and the power in the jet, you find a radio scaling, which actually allows you, so the radio flux scales with the jet power and the accretion rate to the power 1.4, and that seems to explain radio cores across entire range of accretion rates that we see in low luminosity AGN and also powerful quasars. So that is a very unique, ubiquitous and general theme that seems to work and explain radio cores quite a lot, quite well. I didn't have enough sleep. So anyway, so the question is, of course, we think we have a black hole in our galaxy as well. So what do we see there? And in fact, we do see a flat spectrum radio core. This is a large-scale radio emission. There's not much evidence of a jet there. But if you zoom in, you see a supernova remnant, and you see actually hot gas spiraling around. We have the central few light years here. And now we zoom further in. And then at the very center, actually, there's this famous radio source which was discovered in 1974 by Balak and Brown, a flat spectrum radio core in the very center of the galaxy. But there's no evidence of a jet that you see. There's nothing you see. You see only flat spectrum core. And that's where the discussion has been all about in the last few years. People have made all kinds of models for it. We know there is a dark mass from stellar observations of stars moving in the galactic center. These are sort of 10, 15 years of observations of stars, and they all move very rapidly. The closer you get to the radio source, you can actually show that from the orbits of these stars, there should be 4 million solar masses concentrated in this radio source within a few hundred astronomical units. So this is the best case we have for a supermassive black hole, in the entire universe right now. It's a very, very solid evidence for the radio source being really associated with a black hole. Now what we also have, we can resolve the region with this X-ray emission that you see, in fact, and there's diffuse X-ray emission. This is sort of a zoom into the X-ray region. Diffuse extended X-ray emission around Sagittarius A star, which is hot gas. So we know roughly what the density is. And that hot gas actually is within the Bondi capture radius of the black hole. So, just from you know what the pressure is of the gas, you know what the gravitational attraction is. The gas inside here should actually all fall onto the black hole. It should give you an accretion rate of 10 to the minus 4 solar masses per year. However, that would give you a black hole which should be, or an AGN, which should be 10,000 times brighter than what we see right now. It's not. So for some reason, the accretion rate is much, much lower than this. And one reason for this is probably has to do with magnetic fields. This is a busy plot. I apologize for this. 2 years ago, we found the very first radio pulsar in the galactic center. And it's sort of here at about 2.5 arcsecond away from Sag A star. We measured it with VLBI. We have proper motion measurements. It actually moves. It seems to move with this. These are the errors are the motions of the stars, which seem to orbit around the galactic, the Sag A star, the black hole in a sort of in a sort of disk, and the pulsar seems to fall exactly on the motions of these relatively hot and young stars. So it's likely that this actually is a young pulsar, that this was, one of these stars exploded, became a neutron star and a pulsar, it's now orbiting the black hole. So that's interesting because you can use pulsars to study the mass distributions and time them and so forth. But it was also interesting because we found very strong Faraday rotation in the radio emission of the pulsar. I mean, extremely high, 10 to the 60,000 rads per square meter, which means that the gas is also highly magnetized. Faraday rotation comes if the radiation goes through highly magnetized plasma. So we know that the gas here at the Bondi radius, where we find the pulsar, is actually highly magnetized already. And if you look at Sagittarius A star itself, it actually is even more highly, shows more highly Faraday rotation, 5 times 10 to the 5 radians per square meter. And so what we now know is that we are looking towards a black hole through a highly magnetized plasma that is accreting onto the black hole. However, what we also find is that the accretion rate from the Faraday rotation, I cannot go into the details right now here, but the accretion rate onto the black hole is of order 10 to the minus 8 solar masses per year, not 10 to the minus 4. For somehow, in this process from the Bondi scale towards the small scale, you're losing 4 orders of magnitude in accretion rate. And most likely this has to do with magnetic fields and also the structure of the accretion flow, which is a radiatively inefficient accretion flow. Now, if you look at the spectrum of these radio cores, then they actually look all rather similar. If you look at M87, for example, this is an FR1 radio galaxy. It has a flat radio spectrum and then an optically thin power law here. And these are actually 2 radio sources. One is M81, the radio core in M81. It has a flat radio spectrum and an optically thin power law. And Sag A star is actually scaled on top to show the equivalence. M81 star we know is a jet. M87 is a jet. Sag A star we don't know yet, but it walks like a duck. It quacks like a duck. And to me, this is not a duck. It's actually a jet. So that was the main reasons. This is the basic picture we have We think that actually accreting onto Sgr A is a radially efficient, optically thin accretion flow, which means it doesn't release much energy. Somehow it heats up electrons very close to the event horizon. Probably that's what we think the foot point of the jet is. Then you get a synchrotron component like this, optically thick, optically thin, as I said before. Then you eject this into this jet. You have the gradient in the density, which actually translate into sort of a multicolor jet, right? As I said, there's a high frequency, the blue color, so to speak, is close to the black hole, the red color is further out. If you would see all frequencies at once, that's how a jet would look like with your naked eyes, and you would get then more or less naturally the flat radio spectrum explained like this. And then the high frequency part essentially are relativistic electrons which are accelerated close to the black hole, and they can vary a lot depending on how much you accelerate. In fact, you only need to accelerate 1 or 2% of the electrons into a power law to explain all the X-ray emission that you see at high frequencies coming from Sgr A. The nice thing is you can actually also analytically calculate if I have this peak here in the spectrum, explain this by synchrotron emission, how large does the size have, the source have to be? And that's what we did sort of 20 years ago. And again, you can do it yourself, and you'll find that the size at the highest frequency should be of order of just a few Schwarzschild radii. And that's quite interesting. Putting this together, a higher frequency, you go to the smaller scales, and finding that this small scales corresponds to the event horizon scale immediately begs for the question, now what would we see there? And so we suggested, in this paper which actually was a multi-wavelength campaign on Sgr A, that we could see the black hole against the background of this component with future mm-VLBI experiment. And that was sort of 17 years ago, when this was still, well, actually, the very first 1 mm-VLBI experiment had just been done, in fact, at the Max Planck Institute in Bonn in Anton's group at the time. And so it became really interesting that in fact we might be able to see the black hole. We did some calculations and then suggested that if you have an optically thin emission region around the black hole, what you should be seeing is this shadow, i.e. the photons being absorbed by the event horizon, and this deficit, and that's what we're looking for right now. But of course, and then at some point what you want to do is you want to measure how big this shadow is, and you want to compare this to a prediction of GR. We know the math, we know exactly how big the shadow should be. But in practical life, it will still depend to some degree on what the emission mechanism really is. So it is actually quite prudent and important to know, is this a jet producing the radio emission, or is it a spherical accretion flow? And that will not fundamentally change the shadow, but it will change some of the structures to some degree, right? I mean, the shadow itself is a GR effect, but everything surrounding it, the ring itself, will be modified by the emission model. So I think it is still important to figure out what this source really is. Problem is, if you do VLBI on Sgr A, as Anton already mentioned, it's scatter broadened. Well, that's what you see, more or less, at a different frequency. It's just a blob, right? You want to see a nice jet, or you want to see a shadow, and you see a blob. This is a bit frustrating. And the reason is that the source actually, the radio emission has to go through an interstellar medium, which is turbulent, and the radio emission is scattered. And that gives a characteristic size of the source that you measure, which is proportional to lambda squared. And that's what you see. This here is the size divided by lambda squared, so it should give you a flat line. It's more or less a flat line until you reach millimeter wavelengths. This is sort of 7 millimeter wavelengths. So this is here, 0.7 centimeter, 7 millimeter. And there you see, and as Anton said, we regularly can do 7 millimeter, and actually get the best quality data in this game still from 7 millimeter data. You get very low error bars, and you see that the size actually slightly becomes larger than lambda square. And you interpret this as being due to the intrinsic size, intrinsic structure suddenly playing a role. But that's all the information you get. You get a sort of an intrinsic size measurement of Sgr A, not a real structure. If you do this, what we found here in this paper with Jeff Bauer was that in fact the size was decreasing as the frequency was increasing, exactly as you would expect it in the naive jet model. And then this actually continued with 3 millimeter and 1 millimeter measurement by Shep-Dolman in 2008. And indeed, as predicted, the 1 millimeter size approaches the shadow size of the event horizon. So we now know experimentally what you were expecting from theoretical arguments, that in fact the radio emission is made at event horizon scales. So that's good. And also this frequency dependent of the size is something you were expecting. Now the latest measurements we did, we had lots of 7 millimeter epochs and measurements. In fact, we were trying to look for something else, but we realized that the data quality had improved. Until recently, we only had a measurement of the major axis, so essentially east-west measurements of the structure. But now we also get a good handle. Well, we start to get a handle on the north-south size, also for the intrinsic structure. So what you see here is sort of error contours for intrinsic major and intrinsic minor axis. Note the very different scales. So this goes from 0.34 to 0.37. So this actually is a very narrow range for the intrinsic size. This is what you've seen usually on this plot. But this is intrinsic minor axis as well. And that actually is now constrained to be smaller than the major axis intrinsically. And so, up here would have been a spherical symmetric structure where major and minor would be the same. And so the best fitting one is actually intrinsically a 3-to-1 ellipse. That's as much as you can say. It could be a very complicated structure, but you roughly know it's a 3-to-1 ellipse, roughly east-west, which is sort of a bit suspicious. So this is sort of, this is a 3 sigma contour here, so it could be closer to spherical symmetric, if you like, but the best fitting one is 3-to-1. It's a bit suspicious that it goes along the scattering axis. This is something you worry about, but in fact, as I'll show, there may be other indications that indeed east-west is the preferred axis for this source. So that's quite interesting. And we are down here at 7 millimeter at 12 Schwarzschild radii. The other interesting thing that we've been following up recently is time lags. If you have a radio emission coming from the accretion flow, it will fall in, and so we know from observations lower frequencies are further out, higher frequencies are closer in. So expect fluctuations to go from low frequencies to high frequency if the material is falling in, and the other way, go from high frequency to low frequencies if it's in the jet. And what Farhad Youssef Sadeh actually found right in 2008 in 2 epochs, he saw these 2 bumps, and in fact 43 gigahertz would lead 22 gigahertz. You do a cross correlation, you find about half an hour light delay between those 2 frequencies, and it's about 1 light hour difference in size from VLBI. So the natural explanation is that this stuff actually flows out with the speed of light rather than flows in. And so we followed this up with a campaign where we actually, for the first time, we had the VLA, the new VLA with broadband measurements, and ALMA operating accidentally at the same time. Formally this is not possible, but accidentally VLA was was able to observe at the same time as ALMA was observing. And we didn't have a 20 milligen or a 200 millijansky flare. We had a 50 or 20 millijansky flare as a factor 10 less than the Farhad in his data. So, but you see actually a peak actually evolving as a function of time, and you see actually that it goes from high frequency again to low frequencies. And if I translate that into velocities, so this is sort of a gamma beta outflow of 1. So this is relativistic outflow. This is relativistic inflow. The time lags from these measurements, all the time lags are nicely falling around sort of relativistic outflow with Lorentz factor of order unity, 1.5 to 2 of this order. So there's a moderately relativistic outflow, I would say, from the time lag measurements. We're following this up. There are now 3 epochs that show the same results. And we hope there are going to be more in the near future. But the problem is always we only have a few hours on Sgr A, and these flares take 2-3 hours. So this is a tricky business. Now I want to switch a little bit to theory, because I was explaining the simple, the conical, Blandford-Kunigal jet model. But what do simulations see? And simulations are now very well advanced. You have GRMHD, general relativistic magnetohydrodynamics simulations. And now, do you see jets there? Yes, you do, but they typically do not dominate the spectrum. So what you see here is density contours in the 2D simulations, and you see something flowing out here. But this is density. So the stuff that's flowing out has very, very low density. It's completely empty. And what usually people do, they identify this here, the empty part, the spine, as the jet. And if you try to calculate what the emission is, you get almost nothing out there because there are no particles. And people try to seed them with pairs, but pair production is very low in this region, so it's very difficult to fill this part up. And so what we've been suggesting is that, look guys, you're looking at the wrong region. What you actually need to look at is this interface region here between the spine, the empty region, the fast, highly magnetized one, and this here is the accretion flow. Here, this part, the sheath region, is the interesting one. If you do this, you saw some tracer particles seated in there in the beginning. What you see is that most particles actually flow out here, but at low velocity. The fastest ones flow out in this direction. So the highest kinetic energy output in these simulations actually along the sheath region here, and not the central region. So there is matter. It flows out with the speed of light. It has all the properties you need for a jet. But in most of these simulations, you wouldn't see it. Well, there is another problem, of course. Obviously, the mass outflow range in the jet itself, in the sheath, has to be much smaller than the disk, because most of the material has to be accreted by the black hole. Only a few percent can go out. And one little detail that people don't talk much about in these simulations is that actually the temperature of electrons, the heating of electrons, is completely free parameters. People have assumed so far that electrons, coupled to protons in some way, but it's coupled in the same way all over the entire simulation domain. So these are 3D contours of 3D simulations. This is actually low density, this is high density material. So clearly, if you have the same electron temperature everywhere, then this will dominate always by the disk and never by the jet. You would never see jets. What we've suggested is to say, okay, the actual heating of electrons is happening through magnetic coupling, and this is highly magnetized. This is lowly magnetized. So you have low electron temperatures here, low proton-ion coupling here, and high, actually, order of unity proton-electron coupling in this region. And then actually you get rather different pictures. So this is sort of, having the same temperature everywhere. This is where actually you have a normal ADAF, REAF type accretion flow with, low electron proton coupling here, and then a hot electron jet, which means, proton temperature, electron temperature is the same, and you suddenly see the jet. That's obvious. If you have low densities here, you always have lower density here than here, everywhere, in every age you're in, throughout the universe. So these electrons simply have to be hotter. And if you do this, you actually nicely get these jets. This is a model for Sgr A. This is 43 gigahertz. This is 230 gigahertz. You see the shadow. You see a little bit of jet emission. You say, fantastic, but that's not what I see in VLBI. Well, indeed, but that's because of scattering. I'll have to skip this. This is scattering here at 43 gigahertz. Nice jet in simulation. Scatter this, you see nothing. Okay, so maybe at 3 millimeter you would see something like a little bit sticking out, and only at 1.3 millimeter, even in the jet model, you would start to see the shadow, right, in here. But you could see the shadow, but it's still sort of slightly affected by the emission model. So how we can test this? Oh, okay. One more thing to say, we actually used the same model for Sgr A and scaled it up to M87. We had to scale up the accretion disk, and we made the electrons even hotter. Okay, that's the only difference. And what you then see is actually a beautiful jet, and you see actually a structure, if you make a cut through this, which is limb brightened. You see the edges in the simulations brighter than the spine. And I was very happy to see Anton's image of 3C, was it 3C84 or 48? I forgot, which actually showed this. 84 was a bifurcation. M87 we know shows the same limb brightening here, or edge brightening, in this image by Craig Walker. I had a master student re-reduce some of these VLBI images. You see the same here. In fact, Thomas Krichbaum at 3 millimeter show the same. So in VLBI images, we seem to see the edges. And that's what the simulations show, quite naturally. What I also skipped over is, if you look at what the magnetic field and density gradient is in the sheath, it's r to the -2 for the density and r to the -1 for the magnetic fields. So it's a hollow cone, but it's still a cone. It follows a Blandford-Koenig model. So that's why the simple analytic model works still, even now that we have this very complicated fancy GRMHD simulations. The simple one still works, and we get the flat radio spectrum out of this quite naturally from this. So that's I think, quite encouraging. Now, at 3 millimeter Sgr A star, these are simulations we showed with with scatter broadening. What we want to find, of course, is the spin axis. If it's a jet, then we see something flowing out. We know what the spin axis is. That's very important if you want to test GR, because this is one of the 3 parameters. How is it oriented on the sky? It's not quite so easy. You see here, if you convolve this and fit a Gaussian to it, the Gaussian that you find actually can vary quite a bit. The spin axis is always the same, but the jet will change, so you will fluctuate around. So a single epoch measurement will never tell you the spin, but multiple epochs can eventually tell you spin axis if you do 3 millimeter observations. And so one thing that you might actually see then, if the source is no longer a pure elliptical, you want to look at closure phases. Closure phases are, you just sum up the phases from 3 different telescopes, and they are very excellent probes of source structure, because if you sum up the data from 3 different telescopes, errors you make in calibration at individual stations cancel out. You cancel the error, you subtract the error twice, so to speak, for each telescope, and so the closure phase that you measure in your VLBI data is actually fairly independent of calibration errors. You can measure it fairly accurately. And if you do this, and the closure phase for a spherically symmetric model or point symmetric model is 0, and if you have some structure, it will be non-zero. And for Sgr star, the closure phase has been 0 all the time, because it was simply a spherical or an elliptical source. Now, if you do the simulations for millimeter VLBI with 3 and 1 millimeter, then you see the closure phases could vary from a few degrees up to 10 to 20 degrees. And I'll highlight here these 2 lines, because these are the ones which relate to the 90-degree position angle that we sort of were inferring at 7 millimeter. And that would unfortunately predict just a few degrees closure phases, which is difficult to measure, but you can measure this. This is something we're trying right now. We just had an experiment in May, VLBA plus the LMT in Mexico for the first time, participating in a real VLBI run together with GBT. So we had some of the best, biggest VLBI dishes available, get high sensitivity. And this is the data you get from VLBA only. This is if you include GBT and LMT. The paper is in preparation. I'll leave it to your imagination if you see non-zero closure phases or not. It certainly is not 20 degrees, but it's certainly in an interesting regime for the 90-degree one. The same actually at 1 millimeter closure phases, paper by Vincent Fish, coming out, just being submitted, showing actually that constantly the 1 millimeter closure phases are a few degrees above 0, which would indicate sort of a source structure elongated potentially east-west. So that's interesting stuff that's coming up. And I'll have to skip here. I'll skip sort of a history of millimeter VLBI, and I'll skip my wish of having an additional millimeter VLBI station somewhere in Africa, because that will improve image quality a lot. So I'm not going to say this here, but ask me about this and I'll come to my conclusions, which are that, I think, just the punchline, I think the jet model is currently the only model, I stick my neck out, that naturally describes all characteristics of the radio source Sgr A star, spectrum size and legs, and also scales to other AGN. And so I think that is still something to beat. And yes, well, in the future, I hope we'll be able to image the region better, get to the event horizon, not only test GR, but also, of course, understand jet formation and launching better. This is, an important aspect of this entire game. Thank you. Sorry for...
Thank you very much, Heino. We have some questions. Okay, here.
So since we're talking about very precise measurements, so when you say event horizon, do you say that for a non-spinning black hole or a maximally spinning?
Well, interestingly, the shadow size changes only by 10% if you have spinning or non-spinning.
Okay.
So that's the big advantage.
Because the shadow doesn't.
But the emission structure will change dramatically. If you have this highly spinning black hole, you have more or less a point on one side, a little bit of a ring. If you have a Schwarzschild black hole, it's sort of a complete ring. I think we can already exclude a pure Schwarzschild black hole at this point, because the size is smaller.
Can you go back to the images that you showed from the simulations at various frequencies? Keep going.
Yeah. This one's or
further back to it. Okay, so here we are. So at 1.3 millimeters, what are you actually seeing? What's the emitting structure? Is that mostly the accretion flow?
Well, I mean, the point is that you need the hot electrons. And so they become hot only once you go highly magnetized. So this is already the point where the accretion disk is touching, is going into the flow. So that is sort of the foot point. This is the interaction point. So at that point, it's hard to say, is the ankle part of the foot or the leg? I mean, so that is the base point of jet, and probably not all the disk material. And of the jet at 1.3 millimeter in this particular image, you see a little bit stuff here, so a little bit extended there, but you don't see much jet emission.
I guess to restate this, if you were to switch off the painting of the jet, would the image change?
The image would change. It would become what you would need to do. You would need to increase the electron-proton coupling in the accretion disk. That's what you would do if you switch off the jet. Then you would make the disk hotter.
Or rather, if I change the disk, do I see difference here? Yeah. If I were to change the disk temperature ratio between protons and electrons and keep the jet temperature the same, it will probably not affect the normalization that much. So
you cannot make the disk much hotter, because then, of course, you get a huge ultra sub-millimeter bump. So in that sense, you need to keep the disk at the normal ADAF with low ion coupling.
But there is no normal. We don't know what it is.
Right. I mean, the normal one, I was thinking of the sort of original one. Yeah, the original one, which was envisaged, where you had low electron proton coupling in the accretion flow, and that's what we do here.
In your model, you have a free parameter. TP over TE
right.
is like 25. You probably choose.
Yes.
So if you choose 20 or 30, right. Do you see differences in the image? I guess, can you back out what this temperature ratio should be from the observation that?
Yeah. So we get to a this is a range about 20, and if of course you don't have the jet, they need to go to a TP-TE ratio of about 3. But then you don't fit the radio spectrum anymore, and some of the other characteristics. The size-frequency relation doesn't fit anymore. And, you only fit the sub-millimeter bump. So it's, I mean...
Okay, yeah, maybe up here. Oh, okay, sorry. Hey.
This was a bit discussion for the experts here. I think.
It's a very quick question. I just want to ask, you said there was a pulsar.
Yes.
With that pulsar, can you constrain the magnetic field?
Yes, 8 milligauss.
Huh?
8 milligauss.
But if you don't have a coherent collimated magnetic field, you won't get the jet, right? Does that?
Well, that's an interesting point. I mean, the pulsar is, of course, at the Bondi-Hoyle scale, so where material is accreted, and you don't get this Faraday rotation if you don't have some coherent magnetic field structure, right? Because reversals will destroy it. And so this 8 milligauss is already fairly high compared to the kinetic energy density, so the pressure. So this is already magnetically dominated. If you'd have many field reversals, the magnetic pressure would be even higher, right? So we think that at this scale of the Bondi-Hoyle scale, the magnetic field is already fairly coherent. And in fact, that's what you need in the simulations. In these MHD simulations, the jet only comes out if you have some net magnetic field that you accrete. So that also fits together. So and this is probably the only AGN where we actually measure the outer boundary condition of the accretion flow, right? Because we know the density, we know the magnetic field, and at the Bondi scale. So this is pretty unique.
Yeah. That jet simulation, when you showed, the jet is actually a hollow conical.
Yes.
So that means is that all jets should have a limb brightening feature? Can all?
Yeah.
Means all jets should have a limb brighten, right?
I think initially they probably should, but then of course at some point they will start to interact, and if you go to an FR1, you mix into the external stuff, and I suspect Robert Lang showed images yesterday. So then you probably mix material into the central region. So I don't know what happens on kiloparsec scales. Their environment also becomes important.
Because then it would be how the knots are being also formed.
Sorry?
Such a conical jet when you have hollow jet.
Yes.
So the first thing means all jets should also limb Brighton feature. Otherwise, other thing is the knots. With this jet, how will you explain the knot formation?
Well, you saw actually in these simulations that you had lots of little shock waves going out, and actually they form on the side, and they can be actually on both sides of this hollow cone, and probably if you would follow this, you could explain some of this helical structure you see in some of these VLBI observations, because you see in some observation that these knots go out like on a helix.
Going on to M87 from the Galactic Center, it exhibits, I think, daily TV, high-energy TV variation. How do you try and accommodate that in your modeling of this?
We haven't, because I think they are happening more on this first not A or so. That's what people think. But we have been looking at the X-ray and emission. And yes, I mean, you need a power law distribution. You need hotter electrons to explain the X-ray emission. And the natural corollary of that is that you also get TeV emission and inverse Compton emission. That's true. But we have not fitted that here specifically.
Yeah, but that requires gammas of more than 10 to the 8th. And it has to vary on timescales, I think, of a day. So it's...
Yes, but clearly we know in M87 that particle acceleration has to happen along the jet. So it's not just there, but it actually has to happen where shocks are, because the cooling timescale for those 10 to the 8 gamma 10 to the 8 particles is very short. It's much shorter than the flow speed of the jet itself. And so this particle acceleration is not only happening in the jet core, but all the way along. And so in Not A, for example, it just probably hits some the interstellar medium, and so this is a natural place to make this acceleration.
It wouldn't be hard to make it such short term.
No. At Not A, I don't know, because we didn't simulate Not A. We only simulate the inner 50 or so short-shoot radii. There, of course, it would certainly be possible to make this. Yes.
Okay.
If there is an instability going inside.
Okay, folks, I know this is really great. This is really great, and it's not surprising that Heino's talk generated so many questions. But unfortunately, we do need to go on now. So catch him during tea, okay?